Okay, so problem 23 is non-abundant sums. Now this sounds a little bit complicated, but basically what we need to do is factorize numbers, and if the sum of its divisors is greater than the number, then it's an abundant number. And what we need to do is sum all the numbers that cannot be written as the sum of two abundant numbers. So I'll explain this as we go along, but if you want to read the actual outline of the problem, here it is. So how I'm going to do this is, first of all, we need to find main. Now we're going to have a list of numbers, and this can be empty, and then we're going to have a list of abundant numbers. This is going to be also empty, and now I'm going to populate this list, and basically once I've found these abundant numbers, we're going to start crossing off any numbers that can be written as the sum of two abundant numbers, and then whatever's left, whatever can't be crossed off, can just be summed and will give us the answer, or at least that's the plan. So let's populate these lists. So for I in range 20, so in the problem, in the outline, it gives us an upper bound of 28,123. So we're going to use that as our upper bound, so we don't have like a infinite loop. So 28,123, but obviously this uses zero indexing, so we're going to have 24. And we should actually start at 1 as well, so we don't get the 0 in. List of numbers dot append I. If I print list of numbers and I call main, you see we get all these numbers and they start at 1. Where are we at? There we go. So they start at 1 and they end at 28,123. So perfect. Now, once we've got the list of numbers, we need to populate the list of abundant numbers. So to do this, we're going to make another function. So define factorize. It's going to take a number and it's going to return factors. So factors is going to be equal to a list, and what we're going to do is we're going to say so we're going to say x is equal to 1, then we're going to say while x is less than number. I'm also going to have to put brackets on this because I don't like it without them. While x is less than number, if number mod x is equal to 0, then we know we've got a divisor, so we can say factors dot end x, else x plus equals 1. Actually it's not going to be an else because we want x plus equals 1 no matter what. So x plus equals 1. So we're going to return factors. Now what we're going to do is we're going to say test this is working, print factorize, and then we'll give it 10 to do. So let's see what we get. We should expect to get 1, 2 and 5 hopefully. We might also get 10, but I'm not sure, we'll see. So 1, 2 and 5, perfect. We didn't actually want 10 because we don't count them. As you can see right here, when we are taking the divisors of 28, we don't actually count 28 as a divisor. So yeah, perfect, this is what we want. So once we've got these divisors, we need to find out if it's an abundant number. So we're going to say For I in list of numbers, if I is less than the answer to so factorize will return a list of factors, so we're going to say sum factorize and then I. So if I is less than the sum of its factors, which makes it an abundant number, then we're going to say list of abundant numbers dot append I. Now hopefully this won't take too long to run, but I could see it taking a while. Let's just check. So what I might have to do, I might have to go back and steal some code from old problems we've done. I did like a factorizing one previously where it takes into account the square root of numbers. Go look it up if you don't know what I'm about, but basically it speeds up factorizing numbers quite a lot. I also need to check that we're not actually in any infinite loops, but I don't see why we would be. Pretty sure it's just the computation time factorizing numbers, because it takes ages. So what I'm going to do, I'm going to take out the 4 off the end, so we'll make this a really small list. There you go, we see we get all these abundant numbers. So yeah, it's just the fact it's taking a while. Is there any speeding up we can do? It probably is, but it's all, is it going to be necessary since we're not actually going to need to run the whole lot of code many times? I could speed it up later on if it becomes an issue, so for now we'll just go on as if it worked, because it did, it just worked out a small number. So what we're going to do now is we're going to say for, we're going to call it number, so for number in list of numbers, and then we're going to say so we need some way of taking numbers off, basically taking numbers out of our list of numbers. We don't actually need to cross them out though, we could just move them, I guess. So we could have for number in, okay, rather than having a list of numbers, I think that was the wrong way to do it. I think we need a list of abundant numbers. And then we need, so we're going to say this is number 1, and for number 2 in list of abundant numbers, we need to total equals sum of well, we could just actually just say number 1 plus number 2. Now we need to say if total in list of numbers, list of numbers dot remove total. I think that works. Let me just quickly Google this. Yeah, so pretty certain this is how it works. Now what this is going to do is it's going to brute force check basically every combination of numbers, of the abundant numbers anyway, what their sum is, and then if that sum is in our list of numbers, it's then going to remove it. So it is basically just taking them all out of the list. And right at the end we want to print some list of numbers, because now this list should be incredibly short. I'll also just for curiosity print out the list of numbers, and now this will take a little while to run because of the factorizing issue we were having, but it should give us the answer. Hopefully it doesn't take us too long. I'm actually, while this runs, just gonna cancel this a sec, and because I've actually done this before, I did it a long time ago, as I have done with a lot of these problems. I'm just gonna check how I did it before. So this is how I did it before. So I used a dictionary. Okay, so it looks like I did basically the same thing. I just used dictionaries for some reason. Not sure why I used a dictionary, but I did. I wonder how long this one took to run, because I would imagine it's like on par for runtime. It seems to just do exactly the same thing, but use a dictionary to store the numbers that we're going to sum, maybe? Was it? Yeah, so basically just uses a dictionary to store the numbers that we're going to sum at the end. Why did I use a dictionary in this? Alright, so it's to check. So I think I did the opposite thing here. I just added numbers as they were needed, rather than like taking them away from the list. Interesting. I'm guessing it worked. So right now this is taking ages to run. This is frustrating. I'm actually going to open up a new command window and just see how this other one runs while we wait. So I'll just set it away, we'll see if it finishes first. By the looks of it, they're both going to take a while, because I would imagine that they both take like pretty much the same amount of time. This could be interesting, this could be something I try to improve, but I don't actually see a faster way of doing this. I'm sure there will be, but I don't see it. Because it's this factorizing the numbers that is the problem. Because we're kind of like, we've got a list of numbers, like 28,000 numbers, and we're trying to factorize every single number, which will return like in its own like lists that we're then going to loop over and sum. Yeah, it's just not very fast. What I could do is if I add time and if we do this, we take off this 4. Okay, so my other one actually just finished. My my previous code with the dictionary. So maybe it's just way quicker to use a dictionary and that's why I did it. Maybe. Why is that one so much quicker? Interesting. So we have our number to sum to, we have our test number, we have addictive numbers which starts out empty, and then we say for I in range number to sum to addictive numbers I equals I. So this is basically filling the dictionary and saying 28,000, like for example 1 equals 1. So the dictionary would just be like 1, 1, then 2, 2, and then 3, 3. Then we have a list of abundant numbers, and we say for I in the range number sum to is 28,000. X equals factorize I. So we are factorizing. So factorize returns the sum straight off because of this. This is then used to check if it's an abundant number, and if it is, it's appended. Then we just loop over the list twice, and if this sum is in the dictionary of numbers, then we pop it out. Oh, so we are using the exact same method basically, but with the dictionary, because we are popping out the sums as well. So why is it so much quicker to use that dictionary? I don't actually understand how this hasn't finished running yet. I also made a mistake in this one by the looks of it by doing it to 8,123, it should be 24. Interesting. Like, I know dictionaries are better for like doing lookups of stuff to check, like for example when we check down here, if it's in the dictionary, it is way quicker to do that than it is to do this. I know that, so if this was slowing us down, then that would be the reason, but I don't actually think it's because of this. I thought it was to do with the factoring. So if I print factoring done right there, So what I'm doing at the minute in the other command window, I'll capture this so you can see it one sec. So this one right here, I'm just going to run like the new code and basically just going to make it smaller, print out the time it takes to run and see how it scales. So it is the actual going through the list that's taking ages, because like see how that takes 6 seconds. We run this again, the factoring's done like almost instantly. So it is actually the going through the list. If I get rid of this, it is this bit right here slowing it down. Interesting. So that's why dictionaries work quicker. A dictionary, since I've not covered this before, basically is like a hash table if you used any other language, and it looks things up basically by like, you're probably better off looking this up actually. I can't really explain this quickly and I'll come back with it that will make sense, but basically it's better for looking data up than lists are, significantly better, as you can see. So what I'm going to do, I'm going to put this number back to where it should be, and save that, and then I'm going to run this and see if factoring is like reasonable. Okay, so it's still taking a long time, but I suspect once the factoring's done, that if it was a dictionary, it would then be extremely quick once the factoring was done. That's factoring done. So right about now we would get an answer, but obviously that isn't going to happen right now. So what I'm going to do, I'm going to change the code to include a dictionary, like my previous solution did. So what we need is we need this thing right here, list of numbers, to be a dictionary. So we're going to say list of numbers, dictionary, I in range here, list of numbers, I equal to I. Then we're going to say, so for I in list of numbers, dot, so obviously keys, this works. And then total in list of numbers dot value, values. How did I do this? So if it was just in there, then I popped it. Cool, let's do that I guess. I should probably rename this list of numbers as well, since it's not a list anymore. I'm going to call it addictive numbers. Okay, so I could probably just get rid of this as well, to be honest. If the total is in addictive numbers dot pop the total. That works out how I did this. Yeah. And print adjective numbers and print the sum of adjective numbers dot. Actually, does that work? Let's see. Let's get rid of this digit so it's a bit faster. And let's bring this one back up since we're working on this one now. Yeah, so there we go. That is way quicker. Now if I bring back that 4. So this is the actual number that we're using now. Come on, don't take too long. Should be done any second, I would imagine. Oh, okay, so it's gonna actually take a while because of this print. I'm printing the huge dictionary, I think. I know, there we go. So it takes like 50 seconds, which is not ideal, but we do get the answer, and the answer is right. If we look right here, 4179871, 4179871, so it is right. And yeah, if you ever needed an example of where dictionaries are useful, stuff like this is perfect for dictionaries. It confused me at first when I read my old code because there's no reason really with having two tied values to each other. But just for looking data up, just for looking things up in a table, it really makes sense to put them in a dictionary since that's what it's made for really. And yeah, you can tell like this other one is still actually going. This one right here, still going, still hasn't finished. I might leave that running just for curiosity's sake, see if it finishes anytime soon, but yeah, that's going to be it for now. It's going to be it for this video. Apologies for the huge gap in the middle. We were just waiting and I was trying to figure out how to speed it up. But yeah, we got there in the end, and this is probably beneficial to a lot of people, I'd imagine. I know I learned a lot from realising how much faster they were. So yeah, thanks for watching, and I'll see you in the next video.